Section 3.5 is titled Exponential and Logarithmic Equations. And so what we're going to do is we're going to look at two different types of equations for each, exponential and logarithmic. And we're going to talk about how to solve them, and then we're actually going to solve a few. In a previous section, we had solved some word problems, some application problems using our calculator. And this time we're going to look at some of those same types of application problems, and we're going to solve them algebraically. So to get started, we're shown two different types of exponential equations. Okay, what's the big difference between the two? Well, here for type 2, we have a base and an exponent equal to, on the right hand side, a base that's equal to the first base, and then we have some different exponent on the right. Okay, you can notice that we have a function on each side in terms of our exponent, and this one's labeled u of x and the one on the right is v of x. Well, this one's real simple. We just drop the bases because the exponential function is 1 to 1. That tells us that the exponents have to be equal. So we just drop the bases and we set the exponents equal to one another. Type 2, a is our base, so what we have on the left is a base with an exponent, and then on the right side, this is set equal to a constant. Okay, the base a on the left is not repeated on the right. This is just simply a number on the right hand side of the equation. With this type of equation, we simply convert it to a logarithmic form of the equation and solve it that way. And that's what B and C are telling us to do. B, you can see that we just simply take the exponents u of x and v of x and set them equal to each other, and we have a more simple equation. And then C is referring to type 2, where we have a base with an exponent equal to a constant, and so we just take the exponent and set it equal to the log with a base a and the argument c. Okay, and we've looked at this procedure in the previous problems, converting back and forth between. So over here we have the exponential version, and this is the logarithmic version of the same equation. Okay, so with example 1, okay, and remember the remark, good way to double check your solution. You can always solve these equations graphically. And so with example 1, that's what we'll do. We'll solve it algebraically and we'll confirm our answer graphically. A, if we look at A on the left, we have an exponent, a base 3, with an exponent x minus 1. And then on the right, we just simply have a constant. So this is exponential equation type 2. And so what we do is we convert it to a log equation. So we write a log on one side of the equal sign, and as I stated in previous sections, I say that a log equals an exponent, and so what we do is we put log on one side of the equation, the exponent on the other, which is our u of x, and then the right hand side of the equation will become our argument of the log, and the base of the exponent, the 3, becomes the base of our log. And so when you look at this, log base 3, 5, this is a number that you could calculate with your calculator. Okay, so at this point, the variable is only in one place. It's on the right hand side. We can isolate it by moving the 1 to the left side, adding 1 to both sides. On the right, the 1's would cancel, and we would get for x log base 3 of 5 plus 1. Okay, we now have x equal to some number. So at this point, this is our exact solution, because log base 3 of 5, it's going to be an irrational number that we're going to have to estimate if we want to write out a decimal answer. So we bring up our calculator and we can calculate base 3, argument 5, add 1, enter, and we get approximately 2.465. And so we've rounded our answer. This is no longer exact, but let's follow the instructions and try to solve it graphically now. So what we're going to do is we're going to separate this equation into two different equations. We're going to write in our calculator y1 is 3 to the x minus 1, and then y2, a separate equation, is simply going to equal 5. So we have the left hand side on one line of the y editor and the right hand side on a second line. We graph these two, and wherever they intersect should be our solution. Alright, so we go to our y editor, we type in 3 exponent x minus 1. I don't need the parentheses. Enter. And then on our second line we enter 5, and now we graph it. So if you see, if you look at your graph, here is y equal 5. It's simply a horizontal line. And here's the left-hand side of our equation. Okay, this is the exponential part, 3 to the x minus 1. So you can definitely see that they intersect right about here. And we can make our calculator give us these coordinates. And we want the x coordinate. That will be the solution to our equation, because we already know the y coordinate at that point. It's 5. So I go to second calculate, I select intersect, and then it doesn't really matter where your cursor falls. You just want to select one line. Our cursor is sitting on top of the exponential function right now, so we hit enter, and then you see it immediately jumps to the second line that we have in our y editor, y equal 5. Let me go back and do that again. I hit the wrong button. Second calculate, intersect, we select the exponential, and then you see the cursor pop up on the horizontal line, y equal 5. Enter again, and then it's sort of like the min and max that we've used before. You have to hit enter a third time when it says guess, and we get y equal 5, of course. and then we get our solution 2.46, and if we round it 5, just as we rounded it up here at the top. So graphically, we got the same approximate solution. So this was graphically. Good way to double check your work. B is type 1 of our exponential equations. Somewhat. What you see here is we have on one side a base with an exponent, and then on the right a base with an exponent. However, the bases aren't equal, but this is easily remedied. What we can do is rewrite the 16 on the right hand side to where we have a 4. So what is 16? 16 is 4 squared, and 16 itself is being raised to the power of 2x minus 7. So we can write 4 squared with a 2x minus 7 on the outside of the parentheses. And at this point we apply the power rule, which says that if you have a base with an exponent that's being raised to an additional exponent, then we would multiply these two exponents. So what we do now is we take 2 and distribute it throughout the expression here, 2x minus 7. So 2 times 2 gives you a 4x, and then 2 times negative 7 would give you a negative 14. So we started out with a type 1 equation to where the bases weren't equal, but it's important that they are. So you'll definitely have to recognize situations like this where you can write one base in terms of the other, and in this case we did it by using an exponent of 2. So 16 is 4 squared, and 4 matches the base on the left. Then you combine that exponent with the one you were already given. So it's important with type 1 equations that the bases are equal. Once you get that taken care of, you simply take the exponents. Since exponential equations are 1 to 1, then these two exponents must be equal. Okay, so we just set the exponents equal and get an alternate version of an equation. And this is intro algebra level equation at this point. We just want to get the variable by itself, so I could subtract x from both sides. I'd be left with 1 equals 3x minus 14. The x is on the right, so now I want to move my 3 and my 14 to the left. Starting with my 14, I would add it. 14 plus 1 gives me 15. The 14's canceled on the right, and I'm left with 3x, so I divide by 3, and I find that x equals 5. Okay, so algebraically, we have x equals 5. We could take our original equation and double check it two ways. We could replace x with a 5 and see if it works out. So on the left we'd get 4 to the 6th power. On the right we'd get 16 to the 3rd power. And we could check these two values with our calculator. 4 to the 6th power is, it's hardly any space here, 4096, and 16 to the 3rd power is the same, 4096. So the left hand side equals the right hand side. Our solution of x equals 5 checks out. But what about graphically? As in the previous problem, we simply took our original equation and broke it up into two separate ones. In the y editor, we would write y1 equals 4x plus 1, the left hand side, and then our second equation would be 16 to the 2x minus 7. So you make two equations out of the left and the right. We graph them with our calculator. Okay, they're both entered into the Y editor now, so we select our graph button. We get two exponential curves, and we can't actually see where they intersect. We'll try to calculate the intersection without actually having it displayed on our screen. When you go to second calculate and intersect, number 5, the cursor will jump to the first curve and you hit enter, and then check it to make sure it jumps to your second curve and then hit enter, and it did. It gave us the intersection. Okay. In the previous way that I checked our answer of x equal 5, we got the same y value, 4096, for the left and the right hand side. And then for the intersection, x coordinate is 5, as we calculated algebraically. So graphically, we get the same solution. Okay, and that was done by simply finding the intersection, find intersection of the left and the right hand sides of the equation, and that gave us this solution, x equals 5. And again, of course, you're looking for the x coordinate. C, here we have what looks like type 2. But if you'll check the left, take a close look at it, you'll see that we have a base of an exponent. However, this exponential part is being multiplied by 3. So we don't want to take this form of the equation and try to convert it to a logarithm before we take care of this 3 here. So it's real simple to remedy this 3. The 3 is multiplying the exponent, so we would simply divide both sides by 3. 3 cancels on the left, and we have a exponent, okay, the base, It's completely by itself on the left, and then of course it has its exponent. And then our constant on the right is now a 5/3 instead of just a 5. So this fits our type 2 format up above exactly, where we have a, the base, which is e in this case, some expression of x, and then a constant number on the right. Alright, so at this point we can take this equation and convert it to a log on one side, then the exponent is placed on the right hand side. Log equals the exponent, and now we need to fix up our log with the right base and argument. The base of this exponent was e, so I write it as a subscript next to the log. And then the only thing that we haven't used in this exponential form is the 5/3, and so it becomes our argument. Now a logarithm with a base of e is written as a natural log, ln. So now we have the proper form of our logarithmic equation, and here's x on the right, and we simply want to get the x by itself. Ln of 5/3 is simply a number as a whole, and so we say subtract 1 from both sides, because we want the x by itself and we need to get rid of this 1 and the 2. We subtract 1 first, and we write ln of 5/3 minus 1 equals 2x. And now the x is being multiplied by 2, so we divide both sides by 2. The 2's cancel, and we have ln of 5/3 minus 1 divided by 2 equals x. So here's our algebraic solution. This is the exact one, because if we were to write out a single decimal number, more than likely we'll have to round this ln of 5/3. So this is our exact solution. Okay, we want an idea as to what number it is approximately, so we pull up our calculator. And we go about typing in this expression on the left. We have a ln, and it automatically gives us some parentheses. We place our fraction on the inside, we subtract 1. Now we want the 2 to divide both this natural log and the subtract 1, so I need to insert some parentheses around the top. And now I could divide by 2, enter. We get negative 0.755 if I round it to the nearest thousandths. Okay, and so this is the solution to C. I'm down here below D, but it's not a lot of space to work with. But here is our approximate solution to this exponential equation here. Okay, well, we could double check it by simply splitting our original equation up into two separate ones. This is the graphical method. And in our y editor, we would have y2 equals 5. So bringing up our calculator once again. Okay, I'm going to clear this so we can see our calculator a little better. Clear out the previous entries in y1 and y2. And then on the left we have 3 times the natural exponential, and our expression is 2x plus 1, enter. And then on the right side we have 5. And we enter those into our y editor on 2 separate lines. Then we graph them. And now we simply use the calculate menu and the intersect function. The cursor jumps to, it's going to trace along one of the curves, the first one that we entered in the y editor. So once you check that, hit enter, and then it's going to jump to your second one. And so now we're on y equal 5, a horizontal line. We hit enter again. It prompts us to guess. We hit enter a third time. And here we get negative 244. So obviously I must have done something wrong here along the way. What I can do is go back and double check what I entered into the 2 lines of my y editor. The left hand side is 3e to the 2x plus 1, and then my right hand side is 5, and I entered that into the second line. So maybe I entered this expression into my calculator wrong. So I'll go back to my home screen and I'll retype all this stuff in again. I want the top to be inside parentheses. No, I don't want the exponential, I want the log, so I don't need to hit second. So ln button, and then I have 5/3 minus 1 divide by 2, enter. Okay, so I calculated this wrong somehow. Maybe I flipped my little fraction here upside down. Maybe instead the first time I calculated 3/5 instead of 5/3. So my 2 solutions algebraically and graphically do check out. So this was graphically the intersection. This one. And it's identical to the algebraic one. Alright. So here we are at D. This one doesn't fit one of the 2 types of equations from above. There's a lot of clutter. Okay, we have a 4, then we have a subtract 9, and here is our exponential part, and we want this exponential part to be by itself. There is no other exponential part on the right hand side, so we're likely dealing with the type 2 equation. So we need to rearrange this to where the 3 to the 2t minus 7 is by itself. The first thing we need to take care of is the 9, so we add 9 to both sides. The 9's cancel out on the left, and 11 plus 9 on the right is 20. So we have 4 times our exponential part. We want to get rid of the 4, so we divide both sides by 4. So that on the left we now have the exponential part completely by itself. 3 to the 2t minus 7 equals 5. So like I said, we have a type 2 equation from above, and we are going to solve this by converting it to the log version. So on one side of our equal sign we write the logarithm, and then on the opposite side we place our exponent, 2t minus 7. The base of the exponent 3 becomes the base of our log, and then the last number that we haven't placed anywhere yet simply becomes our argument, 5. So log base 3 of 5 equals 2t minus 7. Need a little more room here to work out the rest of the steps. Alright, so we want to get the t by itself, and we have to add 7 to both sides. So now we have a log plus 7 equals 2 times t, and to finally get t by itself we divide both sides by 2. So algebraically we have t equals log base 3 of 5 plus 7 divided by 2. So we want to approximate this expression, get an idea as to what number we're dealing with. So we need to be careful how we enter this. Let's see, we have log base 3 of 5. If you don't have a log base function on your calculator, then you need to recall from the previous section the change of base formula. So as an alternate way to write this expression, we could write log, and if you have a TI calculator you definitely have just a plain common log button, and so we don't have a log base 3 button, so we do a change of base for the logarithmic part of this expression, and we write log of 5 divided by log of 3. We add 7 to that, and then we divide that expression by 2. So I'll type it both ways just to show you that we get the same exact answer. So here we have log of 5 divided by log of 3. We add 7 to that, and now we divide by 2. Enter. So now I'll do it using log base function. I'll enter 3 for my base, 5 for the argument, add 7 off to the side. I'll go back and put in my parentheses around my numerator, the top part, and so now that whole log plus 7 gets divided by 2. Enter. And either way we get the same exact output from our calculator. I'll round this to 4.232. 4.232, and we could put approximate symbols here, the wavy ones. And we want to double check this. Okay, so we're going to solve this graphically. Alright, so with our calculator, we're going to write y1 as the left-hand side, and y2 as the right-hand side. Y2 equals 11. Try to make some room here so that we can see the calculator a little better. 4.232 is our algebraic solution. And we had t, so let me use the correct variable. T equals 4.232. Alright, so our first entry into our y editor will be 3. 4 times 3 to the 2, and instead of using t, I'll use x instead. Arrow to the right to leave the exponent, and we close our parentheses, so this is 4 times the exponential part, and now we want to subtract 9 to complete the left hand side. And now for y2 we have 11, enter. And to solve this graphically, we just want to find the intersection of these two lines. Okay, we don't see the horizontal part. That's easily fixed by changing the limits of our y max. We can type in a number for y max that's bigger than 11 because y equal 11 is just a horizontal line at y equal 11. So there it is. Okay, it was just beyond the limits of our screen. So with y equal 15, we can see the intersection. And so the question is, what does x equal? So we make our calculator do all the work for us. We go to second calculate, select number 5, intersect. Verify that the cursor is on our first line, enter, and then it jumps to the second one, the horizontal one, enter, and enter a third time, and our calculator tells us that our solution x equals 4.232, which is exactly what we got doing it the algebraic way. So graphically, t equals 4.232. Okay, and in terms of our calculator, we simply use the variable x instead of the original variable t. So this just tells us that t equals 4.232. So a good way to double check your answer if you're trying to solve it algebraically. Okay, E. This is one of the application type problems that we solved in a previous section. We did it graphically then. So now we're going to solve it algebraically. We have A equal, A is the amount at a certain time t, and A naught is the amount that we started with initially. We have several zeros here, 3, 1, 2, 3 to the right of the decimal place, and then 1, 2, 3 times our time. So whenever a living organism dies, then the type of carbon contained inside of the body of the organism starts to transform into a different type of carbon. Okay, it transforms into carbon 14. Well, actually, it's the opposite. Okay, live organism contains all carbon 14, and once it dies, it starts to transform into some other version. So it tells us that we only have 20% of carbon 14 left. So I'm assuming that this sample died. This sample of wood died a long time ago. All right, they gave us a percentage that amount that's left. Okay, this amount, A or A naught, neither one of these are in terms of percentages. Okay, so if we want to use this percentage amount, what we need to do is take our A and A naught and turn it into a ratio by dividing both sides by A naught. And we get this alternate version of the equation. And A over A naught is a ratio. It's going to give us a decimal. And what we need to do is take this percentage and change it to a decimal number, 0.2, and this represents the ratio of what's left. Okay, the amount at a particular time divided by the amount that we initially started with. So A divided by A naught gets replaced by a 0.2. Alright, so this is our equation that we want to work with. We want to solve this. And this is a type 2 equation from above. So I'll make some space. And we're going to take this and convert it to the logarithmic form. We do that by writing the log on one side of the equal sign and then the exponent on the opposite side, which is 0.000123t. The base of our log comes from the base of our exponent, which was e, and then the 0.2 will become the argument of our log. Log with the base e is the natural log, so we can write this as ln of 0.2. And at this point we simply want to get our t by itself, so we divide both sides by negative 0.000123. On the left side, the 0.00123 and the negatives cancel, leaving t by itself. And here we have as our solution ln of 0.2 divided by negative 0.000123. Alright, so what is this? What number is this approximately? Go to our home screen and type in ln of 0.2 divided by negative. Make sure you use the negative symbol grouped with the numeric keys 0.000123, enter, and we get 13,084.85 if we round it to the nearest whole number. And this is in years. So we've just calculated how old this piece of wood is. This piece of wood fell off of a tree 13,085 years ago. Okay, it's carbon 14, and the live sample immediately started to decay to some other form. And based off of the fact that it only has 20% of carbon 14 left, we calculate that it's 13,085 years old. Okay. If you wanted to do this graphically, then we could have taken our calculator, and this is our left hand side, and then typed in the right hand side, separated these two. Y1 equals, I'll put the right hand side first, and then Y2 equals left hand side. Alright, so what does that look like? Bring up the calculator, go to the Y editor. Second exponent, negative 0.000123 x instead of t. And then we type in the left hand side 0.2, enter. We hit graph, and the intersection is going to be way beyond the limits of our window. So let's see, we think the answer is going to be approximately 13,000, so I'll type in 14,000 for x max. And then in terms of y, we have a horizontal line at 0.2, so we could type in 0.3 for y max and graph it. And I should have set the y minimum to 0. Okay, so let's go back. Negative 10 is a lot bigger than 0.3, so our intersection appears in a very narrow slice of the graph at the top. So I'll change y minimum to 0, and now we'll get a better picture of our intersection. Okay, there it is right there. We use the intersect function of our calculate menu. We check to make sure that we are on our first curve, and there's our cursor. We hit enter, it jumps to the second equation, the horizontal one. We hit enter again and enter a third time, and we get approximately the same answer. This is exactly what the calculator returned, but if we round it again to the nearest whole, 13,085. Okay, the population of a town is 14,000 and is growing at the rate of 0.95% per year. How many years would it take for the population to double in size? How many years would it take for the population to reach 90,000? Okay, so we're just going to use our continuous growth exponential equation. A, the amount at some later time, times the initial amount, and here our A is going to represent our population, and e to the kt, this is going to, once t is positive, this is going to be a larger and larger number, and so when we take this larger number and multiply it by our initial amount, the amount at some later time is going to get bigger and bigger as t increases. So we have a slow growth rate here, 0.95%. So we have to take this general form of our growth equation, put in our new values for A, A naught, and K, the rate. So the population of our town starts out at 14,000, so our starting value is A naught, exponential function, and then we enter in our 0.9, well, actually we want to enter the decimal version of the percentage, so not 0.95, we want to enter 0.0095, and I'll write t, since this is based on the amount of years that pass. Okay, how many years would it take for the population to double in size? So we want to double the initial population of 14,000, so in other words, we want A naught to be 28,000. Alright, this is similar to the type 2 with the exception of the 14,000, so we want to take care of that. And the 28,000 was just simply 14,000 doubled. So you would expect once we divide both sides by 14,000, we just get a 2 on the left hand side for double. And here is the form of this equation that fits the type 2 that we were shown above exactly. So we can take this and convert it to the log form. Log equals the exponent, so we have 0.0095t on the right hand side. Our base is going to be e again, so log base e could be replaced with just an ln, and then the 2 becomes the argument of our log. So written in a more proper way, we could write ln of 2 equals 0.0095t. So how do we solve for t in this case? Well, we would simply divide both sides by 0.0095. .0095 would cancel on the right. I'm sort of working my way up to the top here. There's limited space, but from this line, the 0.0095 cancels. We get t by itself, which is what we want, and so the time, the number of years, works out to be ln of 2 divided by 0.0095. So approximately how many years does this represent? Take my calculator and go back to my home screen, and I type in ln of 2 and I divide by 0.0095, enter. And our calculator tells us that that is approximately 73 years. Okay, the second question. This is our solution to I. So I suppose I'll write it up here beside I, 73 years. How many years would it take for the population to reach 90,000? So we need to take our original equation. The growth rate stays the same, 0.95%, which placed inside of our formula, we would convert it to a decimal of 0.0095. And we're not doubling the population anymore. It's increasing to 90,000. So when we doubled it, we said that A at a later time was 28,000. So we need to replace this 28,000 to 90,000. And solve the equation all over again. So at this point, same procedure. We want the exponential part by itself. So we divide both sides by 14,000. We may have to round that. I don't know. Let's see. Calculator, 90,000 divided by 14,000. Enter. Yeah. Okay, I don't want to round anything just yet. So to avoid approximating 90,000 divided by 14,000, we'll just reduce this to 90 divided by 14. Okay, 1,000 into numerator and denominator. Okay, just reduce the fraction. So the 14,000 cancels out on the right, and we are left with the exponential piece only. So now we are exactly in the form of type 2 above. We'll convert this to a log. I'll write it up here at the top. Log base E, which is ln, and then that equals the exponent. We have 0.0095 t. So log equals the exponent, and then 90 over 14 becomes the argument of our log. To get the t by itself, we divide by 0.0095 both sides. And so in the end we get t equals this expression on the left, and I'll write it using the natural log ln. So this is the natural log of 90 divided by 14, and then we divide that by 0.0095. What does that become approximately? How many years does that take? So we hit the ln key, type in 90 divided by 14, and then we divide that by 0.0095, enter, and we get about 196 years. Okay, if you want to see that solved graphically, just look back at one of the previous sections. We had an identical problem in a previous section, and at that time the only way we could solve it was graphically. A mutual fund is paying 2.5% compounded continuous. If you decide to invest $25,000 in this fund today, approximately how long will it take for your money to grow $41,000? Here is our continuous compounding formula. Okay, And our rate K is the 2.5% in decimal form. And how much did we start out with? A naught. Well, we started out with $25,000. Convert 2.5 to a decimal, and we get 0.025. And in the end, we want 41,000, so that's going to take the place of the A amount at a later time. To solve for t, we would now proceed in getting the exponential component by itself. We would divide by 25,000 on both sides. We'll drop the 3 zeros, dividing numerator and denominator by 1,000, so we end up with 41 over 25 equals e to the 0.025t. To solve this, we convert it to the logarithmic version. This is a type 2 equation again. So we write log on one side of the equal sign and the exponent on the other. The base of our log is e, and the argument would be the 41 divided by 25. And then to solve for t, all we have to do is divide both sides by 0.025. So, in the end, this is our exact solution. The 0.025 canceled on the right, and so we would just simply be left with a t on the right side. So let's approximate this with our calculator. And then log base e. It's more properly written as the natural log ln. So all we have to do is hit the ln key, and inside the argument type 41 divided by 25, and then divide that by 0.025. Enter. And we have 19.7, so I'll just round that to an even 20 years. At what rate compounded continuously will the principal have amount $800 have to be invested to amount to $1,900 in 12 years? So I'm assuming we have the same rate from above. 19,000 is the amount we want in t years, and then the initial amount, $800, sits in front of the exponential function. And then the exponent of e is kt, where our rate is 0.025. Okay, at what rate? Oh, no, they're saying that we don't have the same rate. We have a different rate now. So we have, we know k, or I'm sorry, we don't know k, but we know t. It said we want $1,900 in 12 years. So now we replace the t with a 12. So this is k times 12. Alright, we proceed in the same fashion as we did in the previous problems. We get the exponential part by itself, dividing both sides by 800. We would get 19 over 8 if we simplified it. E to the 12k, we put the number in front. Now we convert to the log form of the equation. The base of the exponent was e, and so the base of our log will be e. And the exponent goes on the opposite side of the log, 12k. k is our rate, and 19 over 8 becomes the argument of our log. So to solve for our interest rate, we divide by 12. So k equals ln of 19 over 8 divided by 12. So what does our rate have to be? We're going to round it. We're going to approximate it. We have ln of 19 divided by 8, and then we divide that by 12. Enter. So our rate has to be 0.072. If we convert that to a percentage, we would move the decimal point to the right 2 places, and we would get 7.2%. Okay, if you wanted to solve this graphically, you can go to the Y editor. We would take this form of the equation, (19/8) would go into one line of our calculator. Y2 is usually where I put the constant, and then Y1 would be the E to the 12, and instead of k, we won't bother changing the variables of our exponent or our calculator. We'll just simply use x and just understand that whatever number we get for x represents k in terms of our application problem. Table or graph. Zoom standard. Okay, we can barely see our exponential curve. It's right here and it runs along the y-axis here. So if you want to get a better picture, we could use 0 for x minimum, and in the end our k, which is in terms of our calculator the x, our k turns out to be a really small number, 0.072. So we'll use a small number for x max. I'll say 1. Maybe I should say something even smaller. Let's say 0.5. Enter. So here you get a better look at the intersection, but at this point we just simply go to second and calculate, intersect, hit enter, 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 and we get 0.072, the exact same solution that we arrived at algebraically. So here we are. Now we're going to talk about how to solve logarithmic equations. Type 1, analogous to the exponential functions or equations above, we had an exponential on both sides of the equation. Here for the log, we have a log on both sides of the equation with the same base, a. So if the bases of the logs on the left and the right hand side are equal, then we just take the expressions, the arguments of the two logs, and set them equal to one another. Okay, and this is what comment B is telling us to do below. Then we have type 2. We have a log equal to a constant, and then inside of the log as the argument we have some expression of x. This one we would, in order to solve it, we would just simply convert back to the exponential form of the equation and then solve for x. And once again, these can be solved graphically as the exponential functions were. Remark 3 is telling us that we need to check our solution, because sometimes we can do everything correctly algebraically and get a solution that doesn't satisfy the original equation. So we'll double check it. But here we are, we have a log by itself, x is the argument, it's contained inside the log, and 2 is the base. So there's no numbers on the outside of the logarithmic function. Okay, this is type 2 where we want to convert to an algebraic form of the same equation. The base of our log becomes the base of our exponent, and the exponent is on the opposite side of the log, so this is 2 to the 3/2 exponent, and that equals x. And so there's not really a lot of work to do here. X equals, all we have to do is use our calculator and evaluate that number. What do we get? We go to second quit to get to our home screen. 2 to the 3/2, enter. And so this is the exact answer, 2 to the 3/2. But if we want to round it and get an approximate answer, we could say 2.83 if we round it to the nearest hundredths. 2, and I'll put the approximate symbol here in the place of the equal sign, 2.83. Okay. If you wanted to graph this and you didn't have a log base function on your calculator to where you could put in a log with a base of 2, then you would need to enter on line 1 log of x divided by log of 2. This would be y1, and then y2 would simply be the right hand side of the equation, 3/2, and we merely want to look for the intersection of these two entries in the y editor. So log of x, close the parentheses, and then divide by log of 2, close parentheses, enter, and then 3/2 on the second line, graph. We can see the two lines but not the intersection. I think we can still pull out a value for the x coordinate where they intersect. First curve, enter. Second curve, enter. Guess, enter. It's not going to give it to us. We'll have to zoom out. Okay, x is approximately 2.83. We can start there and enter 0 for x min, and then maybe 3 for x max. And let's see, y min and max, we know it's, let's see, what did we get? Well, y is 3/2, so for y max we'll put in 3. And so now we should get a good view of the intersection, and it appears right there on the far right of our screen. We go through the intersect procedure one more time. Second, calculate, intersect. First curve, enter. Second curve, enter, enter, and we get the same solution that we did algebraically, 2.83 if we round it to the nearest hundredths for the x variable. Okay, so this gave us x equal to approximately 2.83. Alright, another type 2 logarithmic equation. We are simply going to convert this to the exponential form, with the base of the log being the base of the exponent. Log is on the opposite side of the exponent too, so we have 4 squared, and then the argument jumps to the opposite side of the equal sign. Solving for x, we would subtract 1 from both sides, and so we get 4 squared is 16 minus 1 equals 3x, and then we divide by 3. Well, 16 minus 1 is 15, so this is going to give us the solution. Once the 3 cancels, x is by itself. X equals 15 divided by 3, which is 5. If we enter the two sides, as separate equations in our y editor. And if you have to do a change of base, then you would simply write log 3x plus 1 divided by log of 4 with a base of 10 now instead of 4. This would be identical to log base 4 of 3x plus 1. This would go into your y1 line, and then y2 would simply equal 2. So log of 3x plus 1 divided by log of 4, enter, clear y2, y2 should equal 2, and we graph it. Alright, so our intersection falls off of the side of our screen. We go to Window and reset our limits. We know that we want a y max beyond 2, so 3 is good, from 0 to 3. And then we know that we have a good feeling that x equals 5 is going to be our solution, so we'll go out to x equals 8. And there we see our intersection. If we go to second calculate and enter 3 times for the intersection, enter, we get x equals 5 exactly. And that occurs at y equal 2. So graphically our solution is x equal 5. C, we have a log on both sides of the equation with the same base 3. This is type 1, and above we are instructed to simply drop the log base 3 part and set the arguments equal to one another. That yields this equation, and with this one we simply try to get the x by itself, which we can't do in this case. We've got this x squared term. Okay, so this is going to be a quadratic equation, and in that case we want to move all of the terms to one side of the equation. So I add 1 to both sides. I'll keep the x squared where it's at on the right because it's already positive. And so now we want to move that 3x to the left as we did the 1, and adding 1 to both sides gave us 2, so minus 3x. There are no like terms on the right. The 3x cancels on the left, and we have 0 equals x squared minus 3x plus 2. If we factor this, we have x, let's see, minus 2, and then an x minus 1. Negative 2 times negative 1 is plus 2. Negative 2 plus negative 1 is negative 3. And these two factors would give us the answers x equals 2 and x equals 1. Alright, so let's double check these. Let's check them with the original equation we were given. For x equals 1, we get log 3 of 3 times 3 minus 1 on the left. And then on the right we get log 3 of 1 squared plus 1 on the right. The left would be log 3. 3 times 1 is 3. Subtract 1, we get 2. And on the right we have 1 squared, which is 1, plus 1 gives us 2. And so the two sides equal, and x equals 1 checks out. What about x equals 2? On the left we have log base 3 of 3 times 2 minus 1. On the right we have log base 3 of 2 squared plus 1. 3 times 2 is 6 minus 1 would give us 5. On the right we have log of 3, 4 plus 1, 2 squared is 4, and then we end up with 4 plus 1 equals 5, and it's identical to the left hand side, so x equals 2 checks out as well. If we look at it graphically, and we graph the left hand side on one line, y1 equals log of 3x minus 1 divided by log of 3, and then on the second line, the right hand side of the equation, we graph log, and I'm simply applying the change of base to each side because you may not have a log base function in your calculator, or you may not know how to use it. So if we change to a common log, we could write log of x squared plus 1 on the top, and then log of 3 on the bottom. So y1 would be log of 3x minus 1 divided by log 3, enter. Line 2 would be log of x squared plus 1 remember to arrow out of the exponent, then type plus 1 divided by log 3, enter, and now we graph. So right up in here you can see it looks like they're going to intersect in more than one place. We could get a closer look using zoom box. We want to pick the corners of the box. I'll go just above this point here, and down below where it appears that they first touch, and hit enter. And you can definitely see that they intersect in two different places. Alright, if we want to approximate this, we could move our cursor over here and you can see that we land round about x equals 1, which was one of our solutions. And then if we go to the second one, we land somewhere around 2, which was our other solution. If we do second calculate intersect, enter, and we enter the first curve and the second curve and the third curve, it gives us x equal 2. I think if we want the other intersection, then we need to enter the first curve and second curve closer to the other intersection. So I move my cursor over towards the first intersection, hit enter, enter on the second curve, enter again, and then it gives us our other intersection. So it does make, you can find multiple intersections of two lines. You just simply have to enter where the cursor is closest to the intersection that you need to calculate. And so our calculator verifies our solutions of 1 and 2. D, this one we're going to have to combine logs because we have 3 logs, and the only type of equation that we have so with 3 logs in this equation, we're going to have to combine a couple of them. We already have one single log function on the right, and so what we'll do is we'll take these two on the left and combine them into one. And to do that, you have to notice that these two log functions have the same base and they're being added. So when 2 log functions are added with the same base, we can combine them into one. With a base of 2, base of the original 2 log functions. And we can combine them by simply multiplying their arguments, x minus 2 times x plus 1. That takes care of the left hand side. Now we only have one log expression on the left, one log expression on the right with the same base. And when you have this set up for an equation, then you simply drop the logs and set the arguments equal to one another. Multiplying the left hand side, we're going to end up with an x squared term. With a quadratic equation, you want to move all of the terms to one side. So I'll add 5 and I'll subtract 3x in the same step. This results in the equation x squared minus 4x plus 3 equals 0. So now we hope that we can factor this quadratic function. And we can by writing x, okay, for each set of parentheses, x times x gives us x squared. And then for our numbers, we could simply write negative 3 and negative 1. Multiply them together, you get plus 3. Add them, you get a negative 4. And with these two factors, we would get x equal 3 and x equal 1 as our solutions. You set each factor equal to 0 separately and solve the equations, and we get 1 and 3. So let's go back and let's check our answer. We have log base 2 of 3 minus 2, and I'll check the x equals 3 solution, plus log base 2 of 3 plus 1 equals log base 2, 3 times 3 minus 5. Here we get log base 2 of 1, log base 2 of 4, 3 times 3 is 9 minus 5, 4 again, And so here we get two identical log expressions on each side. What do we raise 2 to get 4? Well, log base 2 of 4 is 2. Log base 2 of 4 is 2 again. If we subtract 2 from both sides at this point, we see that log base 2 of 1 should equal 0. And that's true. What do we raise 2 to get 1? A 0. So we could have said 0 plus 2 equals 2. 2 equals 2. X equals 3 checks out. What happens if we replace x with a 1? 1, 1, 1, and now we're checking x equals 1. Well, we have 1 minus 2, a negative 1. And here we get an unknown, undefined value. Okay, negative numbers are not in the domain of a log expression, so this is undefined. And so it doesn't matter what we get for these other expressions. This is log base 2 of 2. This is log 2. 3 times 1 is 3, and we subtract 5. We get a negative 2. Okay, so once again, we get an undefined value in our expression. So x equals 1 is not a solution. Alright, the next one we have natural log. So they all have the same bases. In this one we have two log expressions on the right. If we combine them into one, we could write this as 3x plus 15 divided by x. The two natural logs are subtracted. So if you want to combine them into one log expression, then you would divide the arguments, with the first one going into the numerator and the second argument going into the denominator. At this point we have single log functions on the left and the right side, and so we can drop the natural log and set the two arguments equal to one another. Okay. At this point we have an x in the denominator, so we could multiply both sides of the equation by x. On the right the x's would cancel. The left would give us x squared plus x equals 3x plus 15. With the x squared term we're going to get another quadratic equation. So if we subtract 3x and 15 from both sides, we're simply moving all of the terms to the left. The terms on the right would cancel. We would have an x minus 3x, which is negative 2x, and then a minus 15. Factoring this expression, we would get x minus 5 and then a plus 3. Negative 5 times 3 is negative 15. Add the two together, you get negative 2. If we set each one equal to 0 separately, we end up with two solutions, a plus 5 and then a negative 3. If we double check that with our original equation, we have ln, and if I check x equals 5 first, I would have 5 plus 1 equals ln of, let's see, 3 times 5 plus 15 minus ln of 5. The left side would end up being ln of 6. 3 times 5 plus 15 would be ln of 30. On the right, we could apply the quotient rule of the logarithmic functions. If the two log expressions are subtracted, then we can divide their arguments and just use one log expression, and so we get ln of 6 on the left and the right side. So x equals 5 checks out. Now we'll go back and we will check x equals a negative 3. So we have ln of negative 3 plus 1 equals ln of, we have a 3 times a negative 3 plus 15, and minus ln of a negative 3 in the end. And so we end up with a similar situation as we did in the previous example. ln, or a log function evaluated at a negative value, is undefined. ln of 0 would be 1. At this point, there's really no reason in going any further, but all the other ones would be okay, but that doesn't matter. ln of 0 would be 1, but this one, no, this one wouldn't be okay. We'd get another log function evaluated at a negative number, and so this value would also be undefined. So in other words, x equals 3 is an extraneous solution. We can say x equals negative 3 is extraneous, but it's not an actual solution, a full solution to the original equation. The only full solution is x equals 5. So that would complete section 3.5. I hope the video wasn't too long, but there was quite a bit to cover in this section. Thanks for watching.